Hey Royals, in today's lesson we're going to look at AC and DC generators. So in a previous lesson we investigated the idea of DC motors and we used alternating current in a loop of wire with an external magnetic field. And we used the third right-hand rule to discover that when a force is applied on the loop, it causes it to rotate. And this force was generated because of a current running through the wire. Now, generators utilize the same principle, except that we're not going to put the current through the wire. We're going to force the current in the wire. And then to do this, we're actually going to apply an external force on this loop of wire. So this could be, say, water falling over a waterfall, just like at Niagara Falls, turning a turbine. And that turbine is going to cause current to be flowing through a wire. Now, our pictures on our page here are very simplistic and they are just a single loop of wire, but generally in a giant generator, we'll have many different loops of wires and we can create much higher currents this way. So what we'll do is we will analyze these four pictures here to kind of get an idea of how a generator generally works, and then you can investigate further how a larger generator or something at Niagara Falls would make more electricity. Okay, so let's start here with the very first picture. And for it, we have to remember Lenz's law. So Lenz's law says that it wants to apply a force to impede the motion. So in this case here, if I have an external force being applied downwards on this wire, the wire wants to apply a force upwards on that part of the wire to impede this motion. So it wants to stop that motion. Now, if this is the case, and I look at my external magnetic field, and I'll draw it in here, it's going from the north to the south here, and this is going to be the case in all of our diagrams. If I want my force to be acting upwards and my magnetic field to be running from left to right, then I need to have the current coming towards us in this loop of wire. And I'll draw that in red. So the current needs to be coming down on this side of the wire, and it has to be going up on that side of the wire. Well, how did I figure that out? Well, I'm going to use my right hand rule. So I'm going to point my fingers on my right hand from the north pole to the south pole of these two external magnetic fields. So if I do that with my palm facing upwards into the sky, or upwards on my page here, I find out that my thumb is pointing out of my page. So that's indicating that the current is acting out of this. Now in this diagram, it's kind of hard to see what we're dealing with in terms of what's going on with the brushes. So I'm going to draw this part of my wire to indicate that it's actually touching brush 2, right? And so that's actually this part of the wire as well, and it's touching brush 2. And in this case here, it's going to be the top one that is touching brush 2. And then in this case here, it's the left side of it that is going to be touching brush number 2. Okay, so this will just make it easier visually to see what's going on. So we've indicated that the current has to be running in this direction, and it's going to come out of brush 2 and it's going to flow along my wire in this direction. And that's all because I'm applying this external force onto my wire. Now when it turns 90 degrees, and I'm moving on to the second diagram now, when the wire is actually turned 90 degrees, there's no current. I'm going to write that here, no current. And that's because there is no force causing a rotation here. So there can't be a possible current going on. And for the very first picture here, what I'm going to do is I'm going to say that the current is running out of brush number 2. And I'll call it just B2. Okay? And so this wire is going to continue to rotate. And because of that, I'm going to, again, still have, say, water falling on the right side of my wire, which means that it's going to cause a force to be applying upwards because it wants to impede this motion, which means that my current, and I'll draw the force again as blue, just so that it's consistent with the first picture, my current is still going to be acting in this direction. So it's coming out of brush 1 now. And if that's the case, my current is now acting the opposite direction. Now let's analyze this picture a little bit more again. It's saying that if my external field is acting from left to right, now my fingers point left to right, and my palm faces upwards because of the force on the right side of my loop has to be applied upwards. That means that my thumb on the right side of my diagram is pointing outwards. So my thumb is pointing in this direction, which means that the current is running out of, in this case, brush 1, and it's coming to the counterclockwise rotation. So I notice here that my current is running this way initially. It's 0, and then it's running this way. And again, it's going to keep rotating, and when it does that, the force, the external force, is not acting on my loop of wire, which means that we get no current again. And in the case of this B3, what we had was B3 had current out of B1. And so what I'm seeing is I'm noticing that my current is flip-flopping back and forth from being clockwise to counterclockwise, which is by definition AC current. And to go a little bit further, as this starts to rotate, more and more magnetic field lines go through the center of my coil. And so at the moment that in this first picture right here, the magnetic field lines are actually running along the top and bottom of my coil. But in this picture here, my magnetic field lines are running straight through the middle of my coil. And as the coil rotates, more area is being exposed to that magnetic field, which means that as this occurs, we get something called magnetic flux. The magnetic flux is going to generate voltage. And so as the area changes, that it's exposed to this magnetic field, I get that the voltage is going to change as well. So the voltage is going to go up and down, just like we noticed that the current is going to go left and right. So if I'm counting left as positive current and right as negative current, I go from the positive to 0, because we noticed it was 0 here. So it goes to 0, to the opposite direction, back to 0, back to positive again, because again it's going to the left again. And I notice that my current is ranging from a positive value to a 0 to a negative value, back to a positive value. And it's alternating from either being positive and negative. Now in North America, the rate at which this current is changing is 60 hertz, which means that it's alternating 60 times in 1 second. And in Europe, it alternates at 50 hertz, which means it's alternating 50 times per second. And this actually causes the lights, say in our classroom, to flicker 60 times every second. And the fact that they're flickering so fast, our eye can't actually process that. So to us, it looks like the lights are constantly on, but in fact, the lights are turning on and off so fast inside our classroom. And this is the case when we have those long tube lightings in our classrooms. Okay, so that's the idea of making AC circuits and AC generators. We can actually go ahead and make DC current as well. And how we do that is we are actually going to bring in the idea of a commutator. So you'll remember from our DC motors that the commutator is essentially like a slit inside that loop of our coil, right? So in the case of right now, we can analyze this the same way, and you'll notice that the current will not flip and flop because of this commutator. So again, let's analyze the same circuit the same way that we did before. So our magnetic field is coming across from the north to the south. We have that an external force is being applied downwards, so we want a force acting upwards to oppose it because Lenz's law says that it doesn't like that. And if we set up our right hand again, so fingers point from north to south, our thumb points out of the page so that our palm faces straight up at this point. And if that's the case, we have our current coming out of this and it runs into B2. So the current is running into B2, it comes across the front here, and then it's going to run into brush number 1 and come along my loop in this direction. Right, so currently I have my current acting in that direction. So what happens when this thing starts to actually rotate? It gets to a point where the commutators meet up with the brushes, and that causes no current. So my system now went from having current acting to the left to 0, and I'm going to follow this big arrow. It's telling me to go downwards now. This is at the point when my loop is actually flipped over. So let's start by drawing in what the side of our loop we're dealing with. So if this was this side of the loop, that's now the bottom side of my loop, right? And now if it keeps rotating, it becomes this side of the loop. So it's now in contact with brush number 1. And if it continues to rotate, it's now going to be the top part of my loop. Okay, and I'm actually going to fix that so that you can actually still see the other side of the loop. Okay, so we were at position number 3. In the case of this, same thing happens. The force on the coil wants to impede motion. It doesn't want this thing to rotate. Our external magnetic field is still running from north to south, which means that if I use my right hand rule, I'm still getting current that's coming this way. So now it's still coming out of brush 2, and it's going along and it's following the same path that we had previously. So it's going to come in from brush 1 and it's going to flow in the same direction. So you notice that the currents in picture 1 and picture 2 have the same current. Now what happens is it continues to rotate. Well, it continues to rotate, we're still getting no current. And this is because the commutators meet up with the brushes. So there's a momentary no current occurring in our system here. Now, this is the idea of how we can make a DC circuit. So the DC circuit, if I was going to look at the current, I went from having something that had current, and so we can say that that's a positive. It's going to ramp up to a positive. It's going to come to 0 because at this point we had 0, so it's going to come back, bump, and it's going to come to here. All of a sudden the current comes back, and so we get that it's all going left again, and then it goes to 0 at this point here, so it bumps down, and this continues on and on and on. And you'll notice that the current never went the other direction. So the current increases, decreases, increases, decreases, increases, decreases, but never actually goes the opposite direction. So in this lesson, we looked at how an external force on that loop of wire inside an external magnetic field can cause current to flow inside my wires. Now, this is again a very simplistic picture of a generator. And if you wanted to further investigate this, I would look at Adam Beck's power generation at the Niagara Falls power station.